My name is Zhou Li. I'm a professor from the Department of Materials Science at Fudan University. Today, we're going to have our 190th talk. And the speaker today is Professor Horike from Kyoto University. And we also have 3 panelists today. So first, please allow me to introduce our distinguished speaker today. Professor Satoshi Horike received his PhD in chemistry from Kyoto University in 2007, followed by a postdoc fellowship at the University of California, Berkeley from 2007 to 2009. He returned to Kyoto in 2009 as an assistant professor and has been promoted to associate professor and PI at Kyoto University since 2017. He is currently a professor at the Graduate School of Science, Kyoto University, and the VIST at Thailand. His research interest is the synthesis of glass and liquid states of molecular framework materials. He received the 19th Japan Academy Medal from the Japan Academy and the 90th JSPS Prize from the Japan Society for the Promotion of Science in 2022. He serves on the editorial advisory board of Nano Letters, Inorganic Chemistry Frontiers, and guest editor of Communications Chemistry and APL Materials. With that, the stage is yours. Okay. Professor Horike, please.
Okay, thank you very much for the kind introduction. So my name is Satoshi Horike from Kyoto University. Japan time is 9 p.m. It's the best time for the doing presentation. And also thank you very much for this opportunity to share our recent the research work. I hope you could enjoy for my presentation. So let me share. Okay, hope it goes well. And again, thank you very much for this opportunity. So that let me have about 1 hour for the research topic and recent progresses about the creating the glass materials from metal and molecules. My affiliation is 2. The one is that as introduced at the Kyoto University, Graduate School of Science. And the other one is a BISTEC, which is the university in Thailand, focusing on really the research, which is like a top 1 university in the research in Thailand. Okay, so today's title is actually that dealing with glass materials, but not only the inorganic matters and not only the molecular matters. Before introducing our research, let me introduce the very general some solid materials. We say the minerals. Everybody knows that how the minerals are surrounding the world and attract the people, such as jewelry or some other the purposes. Actually, back to the 1941, a German mineralist categorized the bunch of different minerals as shown here. So you can see that the 1 to 10 different classes of minerals as classifying of the components as like this. One of the very typical minerals is oxide in the earth, which is categorized as number 4. Okay, and depending on the decompositions and the crystal structures, we can actually categorize minerals. And so people may know how distinguish in between the crystal and glass in the solid state. So the left-hand side is describing the crystalline states, and the right-hand side describes the representative features about the glass materials. So in terms of the crystals, so crystal means that the structure is really well ordered as like this. So actually this is showing the one example of the typical kind of minerals, the silicon oxide, dioxide. In case of the crystalline states, so silicon dioxide forms quartz as like this, and the structure is quite uniform. On the other hand, we can also handle the disordered glass from the silicon dioxide as like this, that the artificial glass as shown here, or sometimes we also can get the opal in the other minerals, which is quite different with crystals. We can shape as like a spherical, like a morphology. That's because when we take a look over the crystal structure, molecular structure, so the silicon and oxide are, bridging without the long range order, but kind of disordered structure. So we say this is a disordered matters. One of the very special material class is glass. And sometimes people say that glass is a metastable state. Okay, so this is a very general introduction. How do we think about that either crystal or glass? Actually, that needless to say, glass is everywhere. So everybody is using that smartphone, and maybe last 10 or 15 years, how stable over this display in the smartphone is quite improved because the glass property is improved. So this is one of the example, which is the Gorilla Glass made by Dow Corning, and this was made by oxide. But not only for the very typical the glass made by oxide, but we also can take a look at the glasses in the metallic states or the molecular states. In case of the metal, of course, usually the metal prefers to form the crystal, but if we do that, the very fast quenching, cooling from the liquid state to the solid state, we can get sometimes the metastable states, which is corresponding to the metallic glass. This is the example of the copper, the based metallic glass. So you can see that this melt is going down and so quickly that the quench to form the metallic glass. You also can take a look at this bonito flakes. It's a food, but actually the glass transition temperature is around 25 degrees C. So we also can deal with the soft materials below the room temperature, but sometimes at higher temperature, above the room temperature, we can deal with the bonito flakes at the very soft matters, but below the glass transition is very hard. We can't eat. So the meaning here is that the glass is everywhere, supporting of our daily life. And back to the minerals, as I introduced that there are different 10 categories, such as oxide and borate, phosphates, silicates. But you can also find the last number of 10, the classification is for organic compounds in minerals. So usually people will think that the minerals is composed of the inorganic matters, but clearly some of the minerals is made by organic compounds. So one of the typical organic minerals is shown in this right-hand side. Okay, so this is the crystal structure of woodlites. The another name is calcium oxalate. So you can take a look over this crystal structure. The blue is the calcium, and which is bridged by these organic molecules. You can see. So this is made by coordination bond, not like a covalent bonding or inorganic, ionic bonding, but this is made by coordination bond to make this networked structure in the crystal. Actually, we can see crystals in the Earth. Okay, so even like we have different types of minerals, we also can distinguish the different minerals depending on the coordination bonds or covalent bond ionic bonding. So which means that the chemical bonding nature. So please keep in mind, this is a metal and molecule architecture. And actually the last 20 years, the chemist and material scientist developed one of the unique class of the solid materials we call metal organic frameworks, or like we say MOF. So let me introduce what is like a metal organic frameworks as shown here. So this is just one typical example how to make metal and molecular based structures. So this is a zinc acetate. Okay, so the very popular the metal salt. Actually, this is used for something the color kind of pigment. And you also can see that the terephthalates, which is we use for the PET bottle. And so terephthallate has a capability to form the coordination bond to metal, which is shown in the blue. And so if we do combination of two of them, the carboxylate group will replace to the acetate, and then this carboxylate coordinates to the zinc. Okay, but of course the carboxylate terephthallate also has another carboxylate here. So by doing the bridging in between this metal and by use of these organic molecules, we can have a quite extended and uniform structure as shown here. So you can take a look. This blue one is a zinc metal clusters, and each of them are bridged by terephthallate. You can see the benzene ring in between. Okay, and the good thing is that we often get the very nice crystal, single crystal, I'll show here. So by doing the X-ray structure characterization, we can, definitely characterize the crystal structure as shown here. And based on this crystal structure, we can imagine what kind of the application and materials application can be expected. And so in this case, we clearly can see that the 1 or 2 nanometer pore structure inside of this crystal structure. So we also can make use of this pore to capture some small gas molecules or ions and so on. Okay, so this is a good crystal structure, but when we think about that, whether this type of the structure may form the melt state by heating or glassy state by doing some of the treatment, it has been impossible. Only exists something like a crystal structure, because after making the crystals, usually like organic polymers or ceramics and metals will form the melt state by heating, right? We can discuss about the melting point. But this kind of compounds usually change to the irreversibly something different materials, such as like carbon materials or metal oxide by heating without forming that melting state. Okay, so this kind of compounds didn't have any stable melt state by heating, which prohibits the like a wide utilization of the materials by use of the phase change. And the reason is very simply described as like this, because the melting temperature is that like a ratio in between that delta entropy and delta enthalpy in between that crystal states and melt states. And so this usually this melting temperature is above the temperature of decomposition by heating. So that's why we couldn't find the melting structure of this type of the metal organic frameworks. But so back to presumably about like a 2015 of the year, our group and one group in Cambridge, almost the same time found some specific metal organic frameworks crystals gets melt by heating. And so this case is made by zinc and this molecule to have like a two-dimensional structure. And so you also can see the images. So actually, this is a single crystal of this zinc compound. But if we do that heating, it forms a very stable liquid without decomposition. And then the melt can be quenched, and we can also get this glassy state. This also same thing happens for this another the example made by zinc and this molecule imidazoles. But you also can see that the melting temperature is quite different in each other. So this second example shows the melting temperature close to 600 degrees C, which is very surprising for the molecular structure. And so this opens something about the possibility of this like a metal molecular structure do form not only the crystalline states, but the other melt state or potentially the glassy state. Okay. Very recently, 2024, one of the group in Korea also found this that the dicarboxylate ligand, a molecule with magnesium, provides a structure of MOF, and this crystal gets melt below 300 degrees C. And why I highlight this compound is that commercially using the metal organic frameworks materials is usually composed of this dicarboxylates. So which means even by use of the dicarboxylates and the commercial available MOFs, we potentially can get not only the crystalline, but the glassy states. And actually, this is a scheme by the group in Harvard. So as I introduced, the melting temperature is in the delta S over delta H over delta S, which is like in between the crystalline solid state and the melt state. So by combination of metal ions and the ligands, so we can, for example, reduce over delta S by increasing the flexibility in the ligand, but the increase of the delta S by increasing the flexibility, but decrease of the delta H by tailoring of the strengths of the chemical bonding to realize the melting temperature before the decomposition. Okay. So I would say how like we find and developing the MOF melt and glass, which is a new class of the glass materials. So actually, this is kind of accidental. So let me back to the like some of the existing materials in the solid state. So actually, we have been interested in the how do we design ion conducting the solid materials. The ion conducting solid materials is broadly available, like the battery, fuel cell, electrochemistry. So the designing of the high ion conducting solid is quite important regardless of the fields. The left-hand side is describing the kind of conventional, very high proton conducting solid, cesium hydrogen sulfates. So this is a crystal structure made by cesium cation and surrounding the HSO4 here. So why the proton migrate very fast is that at a certain temperature, this SO4 minus starts to rotate very fast, and then this active proton migrates through this crystal. Okay, so this is working as a very high proton conductors. Right-hand side is another like ion conductor, which is a sodium ion conductor, which is also very important for the sodium batteries. And one of the examples is shown here is the composition of a sodium-2 borohydride. And this borohydride is shown in this green sphere in the crystal structure. Looks like a very big and spherical anion and complex. And in this case, also as increasing the temperature, this borohydride anion starts to rotate. Okay. And because of the cooperative rotation, as a result, the intercalated sodium ion starts to migrate or transport very fast. So this suggests that even in a solid state, if we can control the rotating properties, we can aim to get some ion conductivity in the solid state. And actually, the background of the motivation is as shown here. So everybody knows that the fuel cell, like a vehicle, is one of the most challenging, the energy like friendly device. Okay, and Japan also contributes a lot for the like basic technology for the pure fuel cell vehicle as like this. Maybe everybody may know that the fuel cell is composed of the anode and cathode. And so many people are working on the catalyst of the reduction of oxygen or, the oxidation with the hydrogen. But according to this scheme, this middle materials is working as a proton conductor in the solid state. So we call it a proton conducting electrolyte to have efficient the generation of the electricity. But why the kind of vehicle is not really commercialized widely is one of the reasons is because that these materials, the performance is not really great yet. And the criteria is shown here. So actually the proton conductivity in the solid state should be higher than this value. And ideally, we shouldn't control the humidity management, which means that anhydrous condition to have a very high proton conductivity in the solid states. And to make that a very nice like device, crystal actually that has a very serious limitation in terms of the fabricating of the membrane. And so that, this real application needs a membrane formability and a good interface formability. And of course, that the chemical thermomechanical stability is required to have a very good fuel cell. So this is quite long-term challenges, to have like fuel cell systems, which will be like or not alternative, but the another, the contribution for the energy the issues as well as the solid state to the lithium batteries. And back to the design of the materials that, so we have thought that some of the solid state having something rotating motion would be very important. And so to try to get a very fast rotation in the metal and organic systems, which is as shown here. And so actually this is made by zinc and 1,2,4 triazole and phosphates. So crystal structure is in here. So this the middle one is a zinc 6 coordination, which is linked by this 1,2,4 triazole to make a 2D structure. This blue one is a protonated phosphates, okay? And so this is a crystal structure, but if we do the heating to 120 degrees C, for example, and this like pinned the phosphate starts to rotate very rapidly. And because of that extended hydrogen bonding, so the proton can migrate through this phosphates, the assembly to have a very high proton conductivity in the solid state. So this means that the proton conductivity 10 to power minus 3 Siemens per centimeter without any water and high temperature, okay? So this evidence is that high, rotation in the crystalline states by use of the metal and molecules would be a good try to have a very high proton conductivity. And so actually we were happy to see something like this crystal rotation provides the proton conductivity. But actually this was evaluated at 120 degrees C, okay? But the one wondering was that the rotation and high proton conductivity was studied at the 120 degrees C. But simply, if we do the further heating, okay, so this solid state starts to melt as introduced previously, okay? So which means that even in the crystals, why this melting may form is because of this partial, like not melting, but partial cooperative rotation inside the structure, which facilitates the melting behavior below 200 degrees C. And so that by doing of this like phase changes, as I say that we can fabricate glass or fiber or membrane, which opens more opportunity for this kind of metal organic systems. Okay. So this is something brief, that story that we found based on the curiosity, how, that this metal organic systems forms not only the crystalline states, but liquid states and the glassy states. As like just a brief summary so far, is that by use of the metal and the molecular systems, so we have known in the crystalline states, the metal can bridge in between the molecules, but not only the crystals, but if we can control the glass structure, and we can also expect the various type of the applications. So maybe last year we published one review, and just to check how many of the metal organic frameworks the crystal melts. And so you can see that our library is existing, and more, that this type of the compounds will emerge. So this is a background. All right. So I hope that the audience would understand how we can design, the melting systems based on metal organic frameworks. And so let me introduce several functionality based on these the glass materials. So back to the consideration of a proton conductor in solid state, we need a high proton conductivity, but also very important is a kind of soft property to fabricate the electronic device. And so one of the design of the proton conductive glass is shown here. So in this case, we also utilized ionic liquids, which is like organic salt, organic cation anion salt, whose melting temperature is below 100 degrees C. And one of the example of the proton conducting ionic liquid is shown here, okay? So pink proton can work as a proton conductor, but this cation anion forms the ionic liquid in here, okay? So this like a kind of viscous melt is composed of only this, the ammonium cation and this anion. So, but this is a liquid, so we can't use the solid state, the ion conductor, by use of this state. But we are working coordination chemistry. So again, then take a look of these phosphates, so which is working also as a metal-metal bridging ligand. So just simply, we do that reaction with zinc oxide, just by kind of grinding here, okay? And then that immediately we also can get this glassy solid, so which we expect that the kind of soft solid showing pretty high proton conductor. So some of the property is shown in this side. Okay, first of all, this is a viscosity. This is the y-axis of viscosity and temperature. So as I say that this ionic liquid is a liquid, so we can't deal with solid states. The viscosity is very low, especially for the above 100 degrees C. But as you know, the reacting with zinc, so obviously this forms to solid, and the viscosity goes much higher. But this range is a glass working range, so we can fabricate some membrane or making that a good interface with the electrode. So this is a good fit for the mechanics for the fuel cell systems. By the way, this kind of the compound shows that the glass transition that at negative 22 degrees C. So actually that this temperature regime is not actually the glass, but the supercooled liquid with high viscosity. And the one interesting is that this obtained glass shows the kind of very high proton conductivity as shown here, which is that much higher than the pristine, the liquid ionic liquids. So this is like a starting ionic liquid composed of ammonium cation and phosphates. So this is this x-axis, the temperature inverse, and this y-axis is conductivity. And if the samples that shows that the proton conductivity in the range of 10 to 10 power minus 2 or 10 power minus 3, we can think real application. But after the reacting with zinc, okay, so proton conductivity is really enhanced as like this with solid state formation. So this is good because we can just mix up with the zinc with this that commercially available the ionic liquids to form very good like a proton conductor fuel cell. But we also need to understand of the structure of the glass, which is very difficult. And so we conducted, okay, to understand randomized structure, we conducted X-ray total structure factor, like total scattering based PDF analysis, which tells us that how the middle range periodicity in the structure and the X-ray absorption to understand the coordination geometry around the zinc with the use of the reverse Monte Carlo simulation to illustrate the disk glass structure. Okay, and so this is the X-ray absorption fitting, and as a result, we understand at least in this glass state, zinc forms that like both tetrahedral geometry and also the octahedral geometry to make that the networked glass as shown here. Sorry, it's a bit messy, but in principle, this structure forms a zinc and phosphates to have a three-dimensional structure. And this that the ammonium cation derived from ionic liquid is in the like a pore, and which the support of the very fast proton moving in the structure. And so actually that as we work on that glass materials, we also can think about the like network structure fragmentation. So actually, as far as we work on the crystalline metal organic frameworks, it's kind of the prohibited to discuss about that molecular weight. Even in the polymer chemistry, is the main topic is about how to control the molecular weight. But metal organic frameworks or coordination polymers still doesn't have any discussion about the molecular weight. But if we think about the materials, the properties, molecular weight is very important. So in this case, that we have done the reaction with zinc and this protic ionic liquids. But if we reduce the using zinc ion to be more small, as expected, this like a networked glass structure fragmentation occurs as like this. Okay, and which means that this like networked glass domain gonna be very small, and which may contribute to the differentiation of the proton conducting the properties. And this is one of the results as changing of the using zinc ion amounts. So simply say, if we reduce the reacting zinc amount to be small, viscosity goes lower because of the much fragmentation occurs. So it's going to be more behaving over the liquid state. So which means we can control the mechanical properties for the electronic device. But in this case, good thing is the proton conductivity is quite high regardless of the using zinc amount as like this. So keeping the very high proton conductivity, but changing the mechanical properties. Okay, so depending on the using device, we also can change the mechanics with keeping the very high proton conductivity. And so as a result, by use of this kind of compounds, we fabricated the very fundamental systems of the fuel cell, as shown here. Okay, but the fuel cell is very popular, but still quite difficult to have good performance under the completely anhydrous condition, which means that the humidity to be 0 and above 100 degrees C. Okay, and so this case is like a very small like a fuel cell based vehicle, but actually this small vehicle has the 1 kilogram of weight on the top, okay? And with use of the fuels, this works very well with use of our metal organic framework, the glasses. And this IV curve is shown here. So the open circuit voltage, which is like how performing over the initial voltage is pretty high. And then that we also can get to the high enough amount of the electricity by use of these glass materials. So this is a good things for the for development of the next generation fuel cell systems in the vehicle. All right, and so it's coming about 30 minutes. So let's move to the something about more fundamental, some the recent works. I have discussed about how to design the high-performing proton conductors by use of the phase change of metal organic frameworks with glass. On the other hand, not only pursuing the very high proton conducting material for a fuel cell, but the fundamental another challenge is that how we can control that the ion moving by external stimuli. Okay, so like lithium and proton and hydroxide, even hydride, something like this. If we can control that this kind of functional ions in a solid state can be controlled by external stimuli, such as optical stimuli or some other stimuli. This is very important for the non-electronics, but more ionics viewpoints. So this is not our work, but one example in 2020 is shown here. So that they used one of the metal prototype of metal organic frameworks we call Prussian blue analog, which is very well known. The three-dimensional structure is utilized, and so you can see that the proton migration can be switched on and off by the light. Okay, and the key was this NO moiety can be switched on and off, and which contribute for the forming that extended proton conducting pathway or not. Okay, so this is one of the good things, but several drawbacks is that the responsive speed and the on and off conductive ratio was not very high. So we came up with the idea how that this metal organic framework-based glass can contribute to control the proton conductive behavior by photoirradiation. This is another simple example made by zinc and phosphates and imidazole. Okay, and this is a crystal structure. Zinc and phosphates is forming of this one-dimensional structure as shown here. And in between two one-dimensional structure, you can see this is a disordered imidazolates. Imidazole is sandwiched in the structure. And as indicated by this disordering, so which means that this imidazole in a sandwiched fashion forms very high rotation motion in the crystals, and which also confirms that a very high proton conductivity. And in this case, that's the same as the previous example. So this crystal gets melt. In this case, it's at just 54 degrees C, and we also can get this transparent melt and forms the glass. Okay. And when we take a look of the possibility of proton conductivity switching by the light, the very important is how transparent of this glass. Okay, and obviously this glass shows that the very high transparency, which is almost equivalent to the daily use that the silica glass in the window. And we also can fabricate that very thin film with without any color and transparency. But please remind, this glass has a very high proton conductivity inside. First attempt was 2017, and actually by use of this zinc and imidazolate systems, we prepared a melt by heating, which means like 150 or 160 degrees C, and then we doped small amount of this molecule. Okay, this the molecule's name is a pyranine, and which is kind of famous for the releasing of the proton or catching the proton by UV irradiation, as like this. So that we assumed that the small doping of this pyranine molecule into the melt and quench the glass. So this is, you can see that the glass sandwich with 2 ITO, totally transparent with the good distribution of this pyranine in this MOF glass. And by doing of this fabrication, we checked the proton conductivity by this AC impedance measurements, which we know that the resistivity of the ion conductivity. And by irradiating that UV light, we can see some gradual change of the conductivity, which is good. Okay, so which means that we, in principle, can get that photoresponsive proton conductivity, but the responsive speed was very slow, unfortunately, this time. So we need to improve the more rapid, proton conductive switching. So we changed the system. That we use the same morph, but we changed the dopant from pyranine to this, metal complex. This metal complex, ruthenium metal complex, was also very well known to have a proton and release the proton by UV irradiation. And so this actually works very well. So we doped a pretty small amount of this molecular dopant into the melt state. And you can see that this cuvette sample, this is a glass before the doping and after the doping. Even in the very small doping, so this has a color. So this is transparent, but slightly yellowish color. And after making this doped glass, we measure the absorption, which shows that the obvious change of the metal ligand charge transfer. So this means inside of this glass, that this ruthenium complex gets the proton from this proton conductive glass. Encouraged by this behavior, we fabricated the membrane of the glass as shown here, which is about 6 millimeter in diameter. And then that we shed the light by changing of the power as like this scheme, okay? And the conducted that the ion conducting measurements and the results in shown here. So pristine, the glass with dopant shows that this proton conductivity. But if we, shed the light irradiation with different power, the proton conductivity dramatically increased. So which may suggest something that the dopant and glass matrix has a switching behavior. So this means that this is like a presumed scheme. So this has the morph glass here. And so this has a many proton in the structure. But even in the very small amount of the dopant, so that this ruthenium wants to get the proton from the glass matrix, okay? So that this was confirmed that MLCT changes. And then by applying the UV light on and off, so this has a fast switching, which eventually provides the very rapid proton switching, proton conductivity on and off. So the responsiveness changes also quite rapidly. So you can see this is a y-axis proton conductivity as a function of the time. So as increasing that light intensity as like this, quite rapidly the proton conductivity enhancement and returns back to the original states. And durability is also quite nice. So this means by use of that metal organic framework glass with small dopant can migrate in the centimeter, the monolith or membrane to change with the ionic conductivity. Okay, so so not only that high proton conductivity, but this kind of switching can be possible. So actually so if like this type of the metal molecular crystals shows that the melting glass and the crystal reversibly, we can investigate or we can develop as a material of this type of the morphs from the viewpoint of metallurgy, okay? And so because like a different metal combination to make that like a brass or alloy, polymer A, polymer B, just melt and quench. We also can get the polymer alloy. So this kind of the material design can be possible in the morphs. And so one of the example for the proton conductivity as last topic is shown here. So we have zinc imidazolate, the morph, which has a melting temperature close to 160. On the other hand, so as introduced at the very beginning, so it is also that like metal salts showing very high proton conductivity, which we call solid acids. So these two of them can be mixed. And then we also can develop the phase diagram as like this. So that this right-hand side is a pure cesium hydrogen sulfide. This the left-hand side is a pure zinc imidazole, the MOF. But by controlling the ratio of mixture, simply you can say the melting temperature is pretty changing. And then that we also see that some solidus line. So this behavior is a very typical eutectic behavior. Okay, so by use of this, sometimes we can see that the melting temperature is below 100 degrees C by this combination, and we can expect also the very high proton conductivity. So the scheme is that this MOF and this solid acid would have like a mixing solid state together and melts and quench, and we can also get a glass as like this. And in case of the 1-to-1 mixture, the glass transition is around below that like room temperature. So this suggests that quite high, a wide temperature region, it forms like a supercooled liquid. And the viscosity is also that in between this solid acid crystals and this the pure melt. Okay. So again, that I can say that this is working point and melting point. So working point is that like a viscosity. We usually do that like a glass, the glassware handling. Okay. So and then so by use of this that the eutectic systems, the 1-to-1 MOF and this cesium hydrogen disulfates. So this is the proton conductivity as a result. So with use of these two benefits, we can get a very high proton conductivity in the wide temperature regime, which is much higher than the like parent the MOF glass and the pristine cesium hydrogen sulfate. And again, the good thing is that this membrane can be very simply fabricated by, for example, like a doctor blade. So melt and just cast as like the solid state lithium battery. So we can find very transparent high proton conducting materials. Okay. So this is one of the examples. All right. So I should a bit rush. So maybe I hope that people can understand how that the phase changes of the membrane framework would open up of the methodology to design the materials. And so this is another example, not the ion conductivity, but electronic conductivity. So as I say that like this is one of the oldest prototype of MOF, I would say, which is a Prussian blue. And this is a very clear blue color, which is kind of pigment found in 17th and made by first low transition metal, usually the iron 3+ and cyanide bridging. This is a crystal structure, very beautiful, three-dimensional cubic structure. Actually, in Japan, that also that painting is very popular to use of this pigment. You can see this is one of the Japanese very famous, the illustration showing this fish has this Prussian blue pigment. But actually, that after the finding of this Prussian blue structure, but most of the research about this Prussian blue is only for the crystalline states. Okay. And because they don't have a melting temperature by heating. But so again, this crystal structure has many attractive properties, including porosity, electronic conductivity, sometimes magnetism, okay? So, but as heating of this crystal just decompose without showing that like a melting temperature, but we were eager to get the glass states of this Prussian blue analog. And when we take a look of the literature, so another way of forming of the glass is shown here in the right-hand side. So actually, there are many examples, regardless of the materials, to form the glass by very simple grinding of the solid state. So this is like a rice flour. And so even this is a crystalline rice flour. But if we do that, the grinding of the solid, and it forms the glass. And the digestion inside of the body is pretty different in between the crystal and the glass. So we came up with the idea this kind of grinding could be possible to use to make the Prussian blue glass. Simply, we conducted a ball mill of this crystal of this Prussian blue, and kind of quickly it forms glass. That's lucky. And by also we check the glass transition behavior of this glass. And another interest is that whether even after forming the glass, this three-dimensional network is preserved or not. So we check the various characterization, including the pair distribution function that I introduced, to understand how the correlation of metal-metal is preserved in the glass states. And you can see that this is a kind of preservation of metal-metal. And this highlight the peak is that the copper iron in this structure. Even in the glass formation, you can see that a very clear peak. So which suggests even in the plus-and-blue glass, this network structure is maintained. And encouraged of this, so we needed to check that the other properties. First, we checked the mechanical property in between crystal glass of the plus and blue. So this is the cross-section SEM in between the monoliths of crystal and glass. Obviously, you can see that the grain boundary free in case with the glass, which means that the very soft compared with crystal, and which is good. And again, that by use of the glass powder, we measure the Mesbauer to tell how that the mixed valency of the iron 2 plus and 3 plus coexist, which is very important to have electronic conductivity in the glass. Usually, design of the electronic conductivity in the glassy state or amorphous state is very difficult to design the band structure. But in this case, we still have a quite nice semi-conducting property at room temperature with a kind of the very nice monolithic form. So we hope this kind of the plus and blue, the glass can be used for sensor or other electronic devices. And one recent example in this case is actually that, again, back to this type of the Prussian blue analog, we also can prepare the glass formation by composed of the cobalt and iron here. And the crystal can be formed to the glass states by the bond milling. But after the several investigation, we found after forming the glass, this original saturated coordination geometry of iron starts to form that the open metal site by the vitrification, okay? And with maintaining of the mechanical property of the glass. And for this glass, by use of the extra absorption, the coordination geometry in principle is identical with the crystal structure. And so with the use of the enhanced concentration of the open metal site, and because of the thanks to the different band structure in between the crystal and glass, so actually that in the glass shows that the much that preferable band structure for the carbon dioxide reduction in the glass states. Okay, as shown here. Sorry, a bit busy slide. So by use of this that the cobalt iron glass as an photocatalyst, so we could see that the very high selectivity from the CO2 to CO by photocatalytic treatment. And this is because of that enhanced, we believe, enhanced that open metal sites as well as modulated band structure upon the vitrification. So this is one example for the functionality. All right, so still we are investigating what kind of the functionality would be quite powerful by use of the morph glass. So just one slide, I would also introduce one of the very impressive work from Tianjin University. And so actually they used one of the morph glass we call ZIF62, composed zinc 2 plus imidazolates and benzimidazolates. And actually they conducted mixing with polymer to make something like something pancake, okay? And then further heating, so this polymer will go on to have microporous glass domain as well as mesoporous, structure contributed by the removal of the polymer chain. Okay, so you can take a look of this kind of the scheme. Very high concentration as well as mesoporous something that the domain in the structures like this. And because of, oh, can you see, can you hear? Okay, maybe okay. Can you?
Yes, we can
Can
hear.
you hear?
We can hear.
Okay, good. And so by use of this that the hierarchical porosity, so this is a very impressive work, or even it's hard to believe actually. So this is like a gas separation in between nitrogen and methane, which is very challenging, the gas separation. So simply say that most of the reported data is shown here. So which means the gas permeability is pretty low. But this that the MOF glass membrane has like world record, permeability as well as that high selectivity. Okay, so final topic about my side is more like, so we are dealing with inorganic materials in principle, okay? But a three-dimensional glass or like, kind of sometimes like a robust structure-based glass. But needless to say, the glass, domain also can be existing in the organic polymer, okay? And this is a very text book-based the information. So actually that some plastic back shows some elongation by applying the force. So if we do that no stress, this is just like the schematic the structure of polymer plastics. But if we do the pulling each other, elongation of the amorphous domain, which is like a linear line domain, starts to elongate. And finally, the sharing crystal domain, which has like a plastic deformation. And so this kind of polymer properties could be also possible in the metaorganic framework that I will show. Okay. So actually that instead of three-dimensional structure, but actually the polymer usually it's a one-dimensional structure, right? So we can choose metaorganic framework with low dimensionality. So this is a pretty one-dimensional crystal structure made by copper and imidazoles shown here. Actually, this crystal structure was reported quite a long time ago. But by take a look of this one-dimensional structure with weak interchain interaction, we guess this crystal also gets melt. And then indeed, it shows the melting behavior of like this, okay? And in this case, the melt doesn't form the glass, but you can see this sharp peak corresponding to the crystallization. So this case, rapid melting, but rapid crystallization to avoid glass formation. And so one interest is that at the melt state, that this one-dimensional structure is preserved or not, okay? So that we conducted X-ray adsorption and pair discharge function in between that like crystalline states and the melt state. The story is short, the both of the structure is very same, so which suggests even in this viscous melt, the structure is completely composed of this one-dimensional structure without breaking the coordination bond. And we actually checked the like crystal structure, like a melt structure by viscoelastic property. Okay, and then this footprint suggests that even in the melt, that this coordination bond-based one-dimensional chains are preserved. And more interestingly, that you can see the movie, I hope. So by heating and then we pour this sample in between two sandwiching, and you can see that this sample shows that the very fiber type texture, which is normally impossible by use of the crystalline brittle MOFs. And so this, we believe this is because of that like a coexisting of amorphous and crystalline domain with one-dimensional structure. Okay, and so that we are more interested in how the relationship with organic polymers and let's say the one-dimensional MOF, the phase changes. Okay, and so but encouraged by this like one-dimensional structure formation in the melt. So we actually used this one for the demonstration previously, and this is isopropyl imidazoles, but we also can change that the ethyl imidazoles and to form that a very similar type of the crystal structure. And by use of two melt, we mix up two of them. And if we do that 1-to-1, the anymore they don't do the mixture, doesn't have a crystallization, but a very clear glass transition. And actually this was confirmed by changing the two metal organic frameworks with different ratio in the about 1-to-1. It forms that completely glass. And then that the DSC provides that some of the mixture shows that the one-dimensional metal organic frameworks, the entanglement in the glass structure as like this. So this looks like a more similar to the organic polymer alloy that we are now investigating. So actually so by use of this viscoelastic property for this 1-to-1, let's say coordination polymer or MOF alloy. So this is without any filler, okay? And so you also can see this kind of the fiber or this like a film can be elongated to reach to the close to 30%. So we really can deal with this kind of the materials as a soft materials with controlling the metal organic architecture in molecular structure. Okay. Yes. So this is the kind of the second final slide. So a bit sorry that the last part was quickly going, but so this time I like to share our ongoing work in principle to try design and creating new glass by use of metal and molecules. Okay, and that concept behind is that we have known that some many coordination geometries in between the metal and the ligands, tetrahedral to coordination octahedral. So this can work as a network former of the glass. And if we design reticulation of the linking each other, in principle we are able to design the glass structure as well as the crystalline structure. And because of this composition and assembling nature, we can get the very hard transparent glass to the these soft materials depending on the structure, which I hope that contributes to the real problem in our society, including separation, not only the gas but ion separation or big material separation or soft ionic or electronic conductors or photoresponsive materials. Okay. So thank you very much. We are working in Kyoto and Thailand. And so this is actually my team members, probably about 6 or 7 Chinese great students here. Thank you very much.
Okay, thank you very much, Professor Horike. I think that's amazing work. Very impressive, interesting. And I guess our panelists, before that, please allow me to introduce our 3 panelists today first. Okay, our first panelist is Dr. Fan Zhu. Dr. Zhu is an associate professor working on the atomic structures of glassy materials in Fudan University. In 2015, he graduated from Tohoku University in Japan with a PhD degree in intelligent device materials. Since 2018, he served as a postdoc researcher in University of California, Los Angeles, and a research assistant at Lawrence Berkeley National Lab, during which he received the U.S. Department of Energy Basic Energy Science Program Award, and at LBNL. By using the atomic electron tomography, he predicted the first characterization of the 3-dimensional atomic configurations of amorphous solid. In 2021, he joined the Department of Material Science at Fudan University, responsible for managing the operation of rapid electron microscopy and leading a research team on atomic electron tomography. Professor Zhu has developed various characterization methods for the glassy materials, with papers published in nature materials, physical review letters, and nature communication. And Professor Zhu also received the Outstanding Young Scientist Award from the Chinese Society for Materials Research in 2023. And our second panelist is Professor Wenqian Chen from Shanghai University. Professor Chen is currently an associate professor at Shanghai University. She obtained her PhD from Kyoto University in 2015 under the supervision of Professor Kitagawa. Since 2016, she served as postdoc researcher in Tohoku University and was selected for the Shanghai Overseas High-Level Talent Program in 2019. Since 2023, she has held an adjunct position at NSFC. Her main research focus on the application of environmental functional materials. In recent years, she has published nearly 40 academic papers in high-level journals such as ER, Chemistry, Coordination Chemistry Reviews, Advanced Energy Materials, and Chemical Engineering Journals. And she was honored with the Young Talent Award at the 10th International Symposium on Advanced Glass and received the second prize for the Shanghai Science and Technology Award. Our second list is Professor Jinghu Dou from Peking University. Jinghu was born in Weifang, China, and he studied polymer chemistry and obtained a bachelor's degree in June 2010. Then he moved to Beijing and began his doctoral study under the supervision of Professor Jian Pei at Peking University. Its research focused on pivot effect transistors based on conjugated polymers. After receiving his PhD degree in organic chemistry in July 2016, he became a postdoc associate in a group of Professor at MIT in August 2016. At MIT, he worked on the development of 2D conductive metal organic frameworks for applications in energy research. In September 2021, he moved back to Munich and was appointed as assistant professor of material science and engineering in Peking University. Research in his group focuses on the functional chemistry of organic and metal organic materials. So with that, let's welcome all the panelists to the stage.
Hello, Professor. May I ask some question?
Professor Horike, yeah,
it's a really nice
Tim,
talk.
Go ahead.
Yeah, Horike is a really nice talk. I'm really enjoying it. Actually, I'm working on MOFs for more than 8 years. I read almost all your paper. Yeah. So my first question is, in polymers there are a crystalline region and amorphous region, but in your MOF glass, how are the Short-range order and the long-range order characterized, and what is the skill about long-range order and short-range order? Nanometer scale or angstrom scale or micro scale? Yeah, this is my first question. Thank you.
Thank you very much. Very difficult question. Yeah. So actually, I can't say that any of my answer in terms of the domain size yet. I'm sorry, but I showed some of PDF analysis which can tell us like some periodicity from 20 angstrom to 30 angstrom, and some of the glass shows that the clear correlation like 20 angstrom. So it depends on the system, but we think the crystalline domain may be 2 to 3 nanometer at least, or even like glass. And but on the other hand, we are hoping that the crystal domain and the amorphous or glass domain is mutually attached by coordination bonding. So because this is much thermodynamically preferred. So we really think that really actually polymer, some chains are extended, and some of the chains forms that the crystalline domain but change to amorphous domain.
Yeah, cool. Yeah, thank you. Yeah. So I'm very interested in your about the second part of your work. So in your work on multi-processed pristine blue, right? So the numerous surface defects and grain boundaries lead to very interesting properties. So this is a typical example of transforming an ordered material to into a disordered one, right? So besides catalysis, what other benefits do you think could arise from making an ordered material disordered?
Thank you. So for my long kind of the wish is actually the how do we design of molecular, actually really the electronic conductivity with also the property with flexible mechanical property. And that in case of the 2D metaganic framework showing the pretty high electronic conductivity, sometimes it's difficult because of the amorphization provides that like a planar four coordination geometry may change, and maybe it drastically change the electronic conductivity. But yeah, so in the Prussian blue, luckily some connectivity is still remained to have electronic conductivity, and some are in the porous stuff. So as an application, we really believe that some sensing property for the like a really thin film, and especially if we can integrate this kind of porous electronic conductive Prussian blue system on the top of metal oxide, and which really works as like how we say, like sensitive gas, like a sensoring or electronic electro catalysis. And so, but that's on the way which the application will be quite important.
Yeah. Thank you. So my last question is in your last part. So you show the coordination polymer can even be processed, can even become stretchable. This is amazing, right? And the stretchability is 120%. That's cool. So as we all know, so when we process a polymer like rubber, so usually we add some carbon black to change the processability of the polymer. So what do you think if you combine your MOF glass with some very classic polymer, what will happen?
Thank you very much. Yeah. So we are now really more focusing on that combination with conventional organic polymers and coordination polymer or metal organic frameworks. And so maybe the fundamental curiosity is how really miscible in each other.
Yeah.
And so if they are quite miscible, I think that it opens many opportunity to design really flexible and rubberish porous materials, something
That's
like
true.
this. Yeah. And even it's not completely miscible, but as partly I showed in the work in Tenjin. So if we do, how we say, like binary phase integration, and for example, etching one part, and we also can make that like macro morphology of MOFs, and which also is important to have some hierarchical and combination of different the functionality such as porosity, electricity, or some optical properties and conductivity, something like this. So, but in any case, as you suggested, one very important target is how do we combine over the different materials, especially for the polymers with, let's say, coordination polymers. Yeah.
Thank you. It's a wonderful chemistry talk. Thank you. I'm really enjoying it. Yeah.
And hello, Professor Horike. Thanks for your talk, and I benefit a lot from your talk. From your talk, we know the morph glass is a new kind of materials with potential applications on many fields. And because my research topic is on the structure of amorphous solids, so here are some questions of mine for your talk. The first, in your talk, you emphasize the importance of preparing the glass from the melt. But we also know that we can also prepare the morph glass from the ball milling. So is there any difference between them? Yeah.
Oh,
The
thank you.
structure difference. Yeah.
Yes. Thank you very much. Actually, this is also actually ongoing to answer systematically. And but when we take a look of chalcogenide glass, so many people are already agreed that the structure and property in between the melt quench glass and the ball milled glass are pretty similar. That is my understanding. So in case of morph glasses, that actually the glass transition temperature really depends on the ball milling time. So how we say? I just sorry, I can't show that the exact evidences, but I think property in between the melt quench glass and the ball mill glass is more or less kind of comparable in terms of the glass transition behavior or something structure organization.
So even for the ball milling morph glass, you can also observe the glass transition, right? Because for the melt quench glass, morph glass, you can observe the glass transition temperature, but for the ball milling, you can also observe such kind of phenomena, right?
Yes, that's for the glass scientist, it's a kind of surprising that I often hear. And even the ball mill glass, we could see the very clear glass transition. Yes.
I see. Also, we know the glass materials can be classified into three types: the inorganic, the organic, and the metal glass. So, how do you think about the morph glass? It is a new type of glasses, or just belonging to the three types? Yeah.
That's also an important question for us to survive, actually. So from the viewpoint of the chemical bonding, and sorry, maybe I kind of excuse, but the coordination bond has quite a variety types. So which means variety means that the coordination bond strength is from like a 10 kilojoule per mole to like 80 kilojoule per mole, which is quite like a wide range. And also that connectivity in between metal and the ligand, as I show, is also quite different. But on the other hand, metal oxide usually is just using that like a tetrahedral like systems, and organic polymer. If I'm not like a really misunderstanding, basically it's like a one-dimensional architectures. So for taking a look at both that coordination bond strengths and something like a structure syntone to form the glass structures, I hope we can say it's like a really new type of the glass.
Good type. So do you think is there new science for the morph for the new for the new glass materials? Is there new science or?
Yeah, so that's actually we are seriously investigating for what? And glass science is quite close to the industry application. And so maybe much better than me, like even metallic glass was found quite a long time ago, but the utilization is still kind of limited. That is my understanding. But so for the real take a look of the industry application.
But just in this year, Huawei just have a new mobile phone, and they just use the metal glass as a framework. Yeah.
Oh,
the Huawei.
That's good for us. Yeah.
Use the metal glass. Yeah.
So yeah, I optimistically say, like, so I'm really fundamentally interested to design the structure in the glass. And because when I started the MOF crystal chemistry, nobody thought that the design principle would exist in the metal-organic frameworks. But now we can design.
Mhm.
So if we can design that three-dimensional glass structure, this is fundamentally great. And then that we can approach to the like applications. So, but definitely we need the material stability. And so many of the MOF glass so far doesn't have a like very good stability. Often they will back to the original crystal structure. So
Yeah, okay. So do you think can we use TEM, the transmission electron microscopy, to observe the MOF? Do you think is that possible? Because it is not stable, right? I don't know.
yeah, that's actually maybe probably your expertise. So by use of the very special techniques of the TEM, now we are getting more almost possible to see that the benzene ring in the MOF crystals, right? But by changing to the amorphous state, usually that like thermal stability gonna be lower than the crystalline states.
Yes.
Yeah, so that's I think that one of the biggest challenge to do that direct observation. But totally, I have no idea about the TM. Maybe we need some collaboration.
Okay. Well, yeah,
Yeah.
I also have cooperation with you. Thank you very much. Thank you. Yeah.
Oh, thank you. Thank you, Professor Horike. And it's really a fantastic talk. I enjoyed a lot. Many thanks. So actually, just following the question regarding to the structure analysis by the TEM. Recently, I was also involved in some conference, and we also learned that the atomic image about the MOF glass, maybe it's promising. So I think we should work on this topic. Yes. Yeah. And also one my question is regarding to the you have a lot of glass materials, very systematically introduced them, but how about the property during the glass transition temperature? Is there any changement during the TG?
Yeah, that's right. Thank you. So as far as we work on the proton conductors, well, actually we also work on the lithium conductors, which also works very nice. But I don't know why the reason, but in terms of the ion conductivity, it doesn't change quite a lot, above and below the glass transition. That's actually it's unclear why. But mechanical properties dramatically different. As usual, in between that like a glass transition temperature. So I showed some of the transparent the big monolithic the glass membrane, which usually we prepare just maybe 5 degrees above the glass transition, and for example hot press. And so if we do that, this kind of treatment, even that blue monoliths can be very nicely prepared. So sorry, I think that's a very normal answer, but maybe so far mechanical property is one of the biggest change in between the TG.
Yeah, that's true. Yes, thank you. And
one thing that the ongoing challenging is that to lower down the glass transition temperature. So which means that somebody said if glass transition is much lower than the lower temperature, so like some soft property can be possible even in the like minus 100 degrees C or something. Right. So yeah, if we can extend that like supercooled liquid or lavarish state in the quite long temperature regime, this is also that something interesting application which sometimes cannot access by use of the organic polymers.
That's true. Yeah, thank you. And you also mentioned about some like the optical properties, and so I was wondering how about the lanthanide condition polymers? Is there any possibility that to make the lanthanide condition polymer to the glass? Then yeah, we can to see the optical properties, the difference between them.
Yes. Yeah. Thank you. I think this if we are getting more serious, we can get the lanthanide MOF glass easily.
Or it's
And
or it's too rigid to form the glass.
no, actually, that
Oh.
maybe importance is that like a coordination geometry flexibility,
Yes,
or
yes,
like how labile of the coordination bond.
mhm.
So maybe of course sometimes it's not easy, but by controlling of something that dynamics of the lanthanide coordination geometries, we also can get that the glass states based on the lanthanide morph systems. Yeah.
Thank you. And also you mentioned about the glass, the forming stabilities about the morph glass, and you also have the network former, and how about the network modifier? So because people always ask, so how and what can, because sometimes they want to know what's the easier way to synthesize the CP glass. So usually, do you have any perspective about the network modifiers for the glass forming stability?
Oh, I see. So we have tested some of doping of the metal ions, which may work as the network modifier. But so we have not investigated how the relationship in between the modifier, integration and chemical or thermal stability yet. But you're right. So that for the conventional metal oxide glasses, the melting temperature or the mechanical property can be widely tuned by the modifier. And so I think maybe some of the group in Germany or the Belgium has tested on this kind of approaches. So I think it's in principle it's possible. Yeah, but we also need to think for what actually that in case of the silicon dioxide, usually that if we use only the silicon dioxide, the melting temperature is 1,300 something like this, quite energy consuming. So that we put the sodium or potassium to reduce the melting temperature to like 800 or 900 degrees C.
Yes.
Yeah, but in case of the morph glass, that even highest is 600 degrees C. So I think this approach will be possible, but depending on our the demands.
Thank you. So my last question, because we also mentioned about it for the industrial application, and so I was wondering, because some of your systems you already the conductivity already reached to like -2 Siemens per centimeter, the order, I mean. So how about the stability? I mean, both the chemical stability and also the physical stability for your materials, for your glass type. Yeah.
Thank you for your naive question. And so actually, in case of the proton conductors that I show in this lecture, so that it works very well. But if, for example, we integrate big size of the fuel cell, it doesn't work because, of course, that the fuel cell, the big system would produce the water as running over the electricity generation, right?
Yeah.
And then that water at the high temperature starts to decompose the glass.
Yes,
Unfortunately.
that's true. Yes.
Yeah. So or recrystallize.
Oh, but maybe ZIF62 is very stable. I mean, it's stable even in water, I think.
Yeah, right. So several morph glass, including the ZIFs, is pretty stable to the water. But as far as I know, that they don't have a very nice proton conducting properties.
That's true.
Yeah.
Yes.
But actually, that I have worked with a fuel cell vehicle system for a long time, but the criteria of the fuel cell vehicle materials is very high, especially in Japan. I think too much high.
Yes,
So
that's true.
I think in another country, more seriously to integrate a bigger fuel cell system, I believe.
Yeah, that's true. Thank you. Thanks a lot.
Okay, I think the time is almost there. It's already 9:29, and I think we have a wonderful discussion and amazing talk. So I would like to thank Professor Horike again, and here is a certificate that we would like to send to you from iCANX. And thank you again for your wonderful talk. With that, I would like to have Professor Alice Zhang come to the stage and introduce us to the Davos Summit. Oh, Professor Zhang, you need to unmute first.
Yeah. Okay, am I mute? Okay. Can you see my slides?
Yeah.
Yeah.
Okay, let me do that. Yeah, thank you, Satoshi. Wonderful talk. I enjoy really much, actually. Before your talk, I really don't know more about the moths, moths. So yeah, actually I learned a lot. So thank you so much. I use this time to introduce our event. So I mean, all of you are first on this stage, and we're going to have, months later, we're going to have our first iCANX speakers go together. The names of iCANX Davos Summit will be July 11 to 12 in Davos, Switzerland. So this will be a great event. Actually, the event will be happening right in the place where you every January you look at all the world leaders with the assembly and this Congress Center in Davos. So we have the summit in the same building, in the same venue. So, but our topic is different because they are talking about economic politics. So we talk about innovation, science, technology, investment, management, and entrepreneurship. So short as it's time. So it's time to go Davos. See, we have big assembly because we have organizing committees from all over the world. Everyone was online. So from Africa, from Asia, from Australia, from Europe, even from America, North America, South America. So it'll be a big go together. So we have plenary speakers, including Nobel laureates, president of the academy from different universities, different countries, and university head president from different continents. We have a super topic, scientists. We have a super, kind of entrepreneurs. So will be a big assembly, to get in Davos. So yeah, that's the invited speaker and the VIP list. So yeah, you will see this lovely face, not only scientists, investment entrepreneurs, also have musicians, artists. So we're going to get together. Synopsis is something new. So we have a very lovely young face, exciting stars. So welcome all of you young scientists to be there. And this was a 2 days program. So yeah, the first day we're going to have, the plenary sessions with the super scientists and, president of academics and universities and talk about the future. And we're going to have the Young Scientist Award and, Startup Award and Innovation Award going on. So next day we're going to have, many parallel sessions to discuss about AI, biology, from science to technology, to entrepreneurs. So eventually I will highlight something here is our forum. The forum is, like round table panelists. So we talk more about future of science, from discoverers to the entrepreneurs, covers the how to nursing the young generation, the innovations in our future educations. So healthcare, life science, all this hot topic, stabilities, for the long term of the green societies. Also, we're going to have, cutting edge science and technology, especially focus on AI. And one more thing, we highlight, to have the male and the female sessions for the synopsis. How can we working together to make something, amazing? So the last is our, forum about It's Time. We're going to get different parties, from the whole world and from different areas, to discuss like some brainstorming to get the, many more new ideas how to move on, for the society's future. So we have Young Scientist Awards, innovation world, startup world. We also have the beautiful social, qualified social events. We'll have gala dinners on this top mountain top, the hotels, the beautiful view, the best view, also with a jazz band. We have iCANX jazz band. So we will have a jazz party, so there were a lot of fun synopsis, science, technology, entrepreneurs, artists together. So you will have, many exciting events here. And this was a beautiful setup. It'll be amazing. You'll be there. You'll see how lovely it is. So this will be a totally kind of new event. This was the first year. So welcome everyone, to come to Davos. So it's time to go to the summit. Welcome all of you there. Of course, before we came to Davos, we will, have next week's topic will be Professor Luke Lee, who will talk about nanomedicines. So welcome everyone to stay with iCANX and to go, Davos to have this first summit. So thank you all of you. See you next week and see you in Davos. That's all. Thank you.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, entrepreneurship. Short for it's time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invited you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us, and it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
汽车电子化的迅猛发展正在掀起一场技术革新的浪潮。其万千期待于一身的电子元器件，必须以更高的技术水平和可靠性，为汽车电子化提供支持。多层陶瓷电容器、电感器、高可靠性元器件，太阳诱电挺身而出，肩负起推动未来科技进步的重任。电子元器件的发展与汽车、工业设备和网络时代的发展密切相关。为此，太阳诱电 开始了充满激情的挑战。心怀梦想，无畏挫折，不懈奋斗，为用户、为未来高新技术领域倾力打造、倾情奉献优质的电子元器件。太阳用电将吸引全世界的目光。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第一次 iCANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第二个是科学 science， 第三个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time 是时候了，是时候让我们去达沃斯听这些非常给我们启发的关于未来的这些报告。在达沃斯我们会有3个非常重要的论坛，一个是诺贝尔奖论坛，我们会邀请诺贝尔奖获得者